So from last week, we started this introduction on the Hilbert-Schmidt integral operator, and we saw that all of these integral operators, they're going to be a compact operator on the L2 space. And so now let's talk about why we need this Hilbert-Schmidt operator is the following. So essentially, we want to prove the Peter-Weyl theorem. Basically, we want to show all the matrix units. They are going to span a space that's going to be dense in the continuous functions on G. So what we can do is that we can say, well, if I take any function f inside the C of G, and because we have some kind of approximate unit, I can approximate to show its tense. Well, I have a converging net, let's say K alpha, convolute with F. That's going to converge to F inside the uniform norm. Okay, the K alpha is some kind of approximate identity. And because of that, let's just consider what happens when you do this kind of convolution. So this K alpha is approximate identity. I can make it on the level on the right. Let's actually just make it on the right. All right, so what happens if I want to compute what is the F convolute with some K, evaluate at X, is the following. So this is going to be the integral of the f of x by the formula f of y, the k of the y inverse x, okay, and the y, that's just the convolution. But if I treat this as, well, here I treat x and y are basically two variables, I can treat it as the k of the xy. All right, so this becomes the integral of this k of xy, some kind of the Hilbert-Schmidt kernel integrate against this f of y. So I integrate the y out, and then I get a function in terms of x. So this is just no other than the Hilbert-Schmidt operator of this t transfer of this f. Okay, so evaluate at x. Okay, so this convolution I can always understood it as a Hilbert-Schmidt integral operator. So here, the one of the condition is that this Hilbert-Schmidt operator, this kernel is Hermitian. So that's essentially just requiring the K to satisfy the following. So if I consider what happens if I conjugate that, so that's just equals to the K of the y inverse x, the whole thing conjugate, and I need it to be equals to the k of the yx, okay, which is equals to, on the other side, this x inverse y. And you see this is just flip whatever is in there, the y inverse x, okay? So in other words, if this k alpha, this k satisfies the kx conjugate that's equals to the k of x inverse, then the kernel defined this way becomes a Hermitian, okay? The kxy conjugate is equal to k of yx, okay? And this is easy to do, okay? So if I, for example, this k alpha, I know if I can choose some kind of characteristic function of this neighborhood around identity divided by the measure of this neighborhood, they're going to be approximate identity. And then I can also pick these neighborhoods so that they're symmetric. So because they're symmetric, you can easily verify that this equality is going to satisfy. Okay, so for example, if your k alpha is equals to 1 over the measure of some v alpha times the characteristic function of v alpha, and as long as your v alpha is symmetric, then this condition is easily satisfied. Okay, so that's not something that's too difficult. So basically what we showed is that, well, each of these f convolute with the k alpha, that's just going to be equals to the Hilbert-Schmidt operator on this f. Okay, it looks like an integral. And because this t is going to, we know it's a compact operator, it's also self-adjoint because this k is Hermitian, we have a nice spectral theory for that. Okay, so we have a nice spectral decomposition for this t. Basically, because it's compact and self-adjoint, we know its eigenvalues, or its the spectrum is going to lie on the real, and is going to, each of these non-zero eigenspace is going to be finite dimensional. And moreover, we know something about the eigen, the spectrum is either is at most countable, and it's going to converge to zero if it's not finite. All right. So that's some operator theory. So if I just do the following, so let me just prove the following. So the ultimate goal of this few videos is that we want to show that each of these TF is going to be inside the closure of the matrix coefficients. Okay, so that's kind of our goal. And if each of them is in the closure, then of course the F being a limit of these TF is also going to be inside the closure, and hence we finish the proof of the Peter-Weyl theorem. All right, so that's our goal. So our first technical lemma, I'm going to consider I want to show that their eigenspace are actually just going to be inside the matrix coefficient. Okay, so for every, say, alpha is non-zero, let's consider the eigenspace H alpha to be all the F inside the L2 of G, so that let's fix some K that's symmetric, and I define the integral operator to be this T. So I consider TF is going to have the alpha times F, so this H alpha is the eigenspace of alpha, and we know that all of these H alpha are going to be finite dimensional because of the compact operator. Then I want to show the following. So I want to claim that each of these H alpha is actually, well, as a subspace of the L2 space, is going to be contained in this E, okay? So the proof, so first of all, we know the dimension of the H alpha is less than infinity. That's just the spectral theory of compact self-adjoint operator. And so first of all, I want to show that this H alpha is going to be invariant under the left translation. So if I take the left regular representation and then I restrict to this H alpha, I get a finite dimensional representation. Okay, so to show that, let's consider the following. So let's show the H alpha is invariant for the left regular representation or any LG. All right, so let's say if I take F inside H alpha, okay, and I consider what happens if I left translate my F by, say, a G of F, okay, and then evaluate at X. So we know this is essentially just given by this conjugation. So I left translate my F, and I convolute with the function K, this small k, and then evaluate at X. So let's write out this integral. So we have done these kind of calculations several times already. So let me just write it out quickly. So I have the integral as a convolution, and then the left translation basically just boosts, put a G inverse on the left. Okay, so I have a y inverse X dy. And now I have, I can use the left translation. I can put a G on the left of Y, and then I move the G inverse inside K. So this becomes the integral of the f of Y. So I put a G on the left, so Y becomes GY. So I have a K of the GY inverse, which becomes Y inverse G inverse of X, okay? And this whole thing dy. And you realize, well, this is essentially just the convolution of the function f with k, but evaluate at g inverse of x, all right? Well, if you think about now, the g inverse is on the other side, so it's put on the x. So you think about this, essentially this is the left translation of the convolution of at x, okay? But the convolution, we know this is, by definition, we saw this is the Hilbert-Schmidt operator T applied to F, okay, evaluated at X, and then I left translate this operator. But F being in the eigenspace, we know this TF is going to be equals to alpha times F, okay, so this is just the left translation of the alpha times F evaluated at X, okay? Well, now alpha is a constant, so that goes out. So this is alpha times the left translation of f, evaluated x. So let's see what we prove. So essentially, I prove that if I consider this function LG, so if I apply t to this LG of f, okay, so I got that's equals to alpha times the same vector LG of f. So LG of f, again, is in the L2 space. So I basically show this LG of f is also inside the H alpha. Okay, so H alpha is closed or is invariant under the left regular representation. So now because it's invariant, so I can always restrict it, my left regular representation to a finite dimensional representation. Here the H alpha is finite dimensional. So let's let pi be the restriction. So let's let pi be the restriction of the lambda, the left regular representation, let's call it lambda, on this finite dimensional space H alpha. This is a finite dimensional. So because H alpha is invariant, we know that pi is a finite dimensional, first of all, because H alpha is finite dimensional, and it's a unitary representation because it's invariant, okay, of this G, okay? So I basically now constructed a finite dimensional representation. And so let's consider its matrix units, okay? So if I, let's just let say F1 up to say FD to be an orthonormal basis for my H alpha. And let's consider what happens if I consider its matrix unit. So let's let pi ij of this element G is essentially just equals to the pi of G, okay, evaluate at Fj, and then inner product with the Fi. That's the kind of the basic matrix unit. But pi of G is essentially just the left regular representation. So this is essentially just the left translation by G of the Fj inner product with the Fi, okay? So because this H alpha is invariant, so we know that if I write this pi of G is equals to this n by d by d matrix pi ij of G, okay? So now we want to show that this H alpha is inside E, so they're basically spanned by the matrix unit. Well, it suffices to show this these basic vectors are spanned by some kind of matrix coefficient of some finite dimensional representation. So let's start with any orthonormal basis vector, let's say Fi of Fi, okay, and I consider what is Fi of G? Well, it's essentially just equals to the left translation by G inverse of the Fi evaluate at the identity, okay? So what is the L of G inverse? Well, this is because Fi is in this H alpha and the L restrict to this F, it becomes the pi. So this is essentially just the pi of the G inverse evaluate at Fi, okay? And I have the, this is evaluate at E, okay? So what happens with, if you think about this pi as this matrix form, okay, so you take a basic vector for the ith basic vector. So what you do is that you use the ith column to multiply the corresponding Fi, all right? So this is just going to become a kind of a column vector, and you write it the following. So you write this as a summation of the pi of Ji evaluate at the G inverse of the, so you move the Fi to the jth row, so it becomes the Fj of E, okay? So this is J going from 1 to D, okay? So that's just, you treat this F as the orthonormal basis and your pi as these D by D matrices. And the nice thing about this is that if you think about what happens to these pi Ji of G inverse, if you recall the conjugate the conjugate of a representation is essentially just the pi of the G inverse. You take the transpose. So each of these pi ij is, if you consider pi of Ji of the G inverse, that's just equals to you take the transpose. So it's pi bar evaluate at ij of evaluate at G, okay? So this one becomes essentially just equals to summation J going from 1 to D of the Fj evaluate at identity, and you multiply by the pi bar of the Ij evaluate at G, okay? So if you ignore the G, so the function Fi now becomes a function of, these are just constants, okay? So they're constant scalars. and you multiply a bunch of pi bar of ij. Well, pi is a finite dimensional representation, so pi bar is still a finite dimensional one, so that's going to be inside the E. So my fi is going to be inside the span of all these pi bar of ij. So that's clearly inside the E, okay? So actually inside the E of the pi bar. So I finished the proof that each of these these basic vectors inside the H alpha is going to be inside E. So that just finished the proof that the H alpha is actually inside E as well.